Thank you very much for the short introduction. I'm happy to present my work here at the AppsCon, even if it is one of the very last sessions here. But I'm happy that I see some faces here that I've met during the conference, and I hope I can make some sort of vital presentation. It's not directly related to sports, but it's definitely related to internal load, as we have seen it in the presentation before, to some physiological stuff in human bodies. So my name is Severin Bernhart. I work at the Human Motion Analytics Department in Salzburg, at the Salzburg Research Institute, and I'm doing a PhD at the University of Salzburg in computer science. And this is the team with which we developed this paper. So the title is Textile Moisture Sensors for Estimating Sweat Evaporation Saturation in Fire Protective Clothing. So my question is, has anybody ever worked with a as firefighter, maybe? Or no experiences at all? All right. So I have a little introduction. What is the problem? Firefighters are often have to deal with heat stress, because heat stress is caused by high temperatures and the metabolic work, which they have to deal with during the firefighting operations. So heat stress then causes decreased cognition abilities. So, for example, the risk-taking behavior or the impulsivity changes during the firefighting operations, which then maybe leads them to do wrong decisions during firefighting operations. In addition, the physical ability is limited because performance and endurance is decreased. And this also leads to lesions, fatal incidents, impaired brain functions, and in severe cases also to coma. So I want to explain a little bit what is heat stress exactly. So the natural body cooling happens with vasodilation, so increasing the blood vessels, or sweating due to the evaporation chill. So when people sweat underneath a jacket, then the microclimate air humidity is rising up in the jacket, and this prevents the evaporation. So the cooling effect is no more given, and the body core temperature rises. Therefore, the body tries even more to cool down the body, and the sweat rate increases even more, which then also leads to dehydration. In the literature, we found that the biggest demand of firefighters during their operations is active extrinsic body cooling. There are already some air vests which can provide cooling, and also some water cooling vests, but these never came to usage for firefighting operations because they need some sort of preparation, and if there is an emergency, there is no time for any preparation. So we want to provide an automated cooling with less effort for the firefighter himself or herself, and we want to do this with smart textiles. And we believe that we can maybe, or we try to avoid heat stress situations to improve the capabilities of firefighters. Therefore, we came to this goal. We want to develop a fire protective cooling clothing within the project TechSense. You can see it on the Salzburg Research homepage if you want to. And in the end, it should be able to detect sweat, to trigger an automated cooling algorithm, which then can avoid heat stress. So this is how our prototype looks like. This is a fire jacket lining with 4 integrated textile moisture sensors. The moisture sensors are basically made out of a cotton substrate with conductive yarns inside. I also have one piece here. If you want to see it later on, you can reach out to me. And the conductive yarns are made out of stainless steel. And we selected 4 different positions at the front, at the elbow, the upper back, and the center back, because these are positions where especially thermal sweating happens. You may know also at the armpit or at the fingers you often sweat, but this is more psychophysiological stress. So when people are nervous, for example. And we connected these textile sensors to a so-called demo hub network. We developed this in-house at Salzburg Research, and it is made for time-synchronized data collections, where you can easily compare different sensor signals at different body locations, for example. And it's perfect for doing rapid prototyping. We did a data collection, which was some sort of, funny for us. We had 19 young male participants. They were supposed to be 30 minutes in a sauna at 60 degrees and with air humidity of 30 to 40%. We controlled the body core temperature that it doesn't exceed the threshold of 38.5 degrees Celsius. And we also checked the hydration status before the experiment. They have worn the fire jacket lining underneath a full fire protective clothing. We also integrated a wireless climate network, which consisted of 4 sensors to have a reference what is the microclimate air humidity underneath the jacket. And they took the body core temperature E Celsius performance capsule the day before, so that we have reliable body core temperature data. The data processing was more or less pretty straightforward. We applied a 0-lag second order Butterworth low pass filter with a cutoff of 0.1 Hertz. We did the missing values handling with the linear interpolation. We did synchronize all the data streams by removing the time offset and downsampled all sensor signals to 1 Hertz and applied a set score normalization for better signal comparison. For the analysis, we applied a Granger causality test, which is an F-test with a p-value to check the significance of the hypothesis. The Varic textile moisture sensor cannot forecast microclimate air humidity. And we also compared the 4 different locations of the sensors. So this is what came out of the data collection. On the upper plot, you can see the reference signals from the microclimate air humidity. In the middle plot, you can see the textile sensor signals. And on the bottom plot, you can see the body core temperature rising during the 30 minutes in the sauna. And when we compare the positions in the table above, we can see that the sensors in the back region had a highly significant result. So they can forecast the microclimate air humidity. And also the elbow and front position was able to forecast the microclimate air humidity, less significantly, but still it was possible. So this leads us to the discussion. We tried to reduce the amount of electronic components. So we want to go in the future just with 1 sensor attached to the back to improve the user comfort and also to reduce the probability of having any technical errors. Another issue we ran into, we didn't expect this. The conductive yarns corroded, even if they were stainless steel, because we applied direct current, and this caused electrolysis, and therefore we have to change the measurement circuit. We will apply alternating current and include another reference electrode to subtract the parasitic resistance changes to have a reliable sensor signal in the future. Future work in the end, we will develop a cooling trigger algorithm that the cooling will be triggered automatically. We also collected some subjective data like vitality, fatigue, rate of perceived exhaustion, thermal sensation, thermal comfort. And we want to detect if there is some change point in the data where we can then derive a threshold in the sweat data. We also collected heart rate and breathing rate data, and we are still in the investigation of this data. We are currently also developing electric valve that can be also steered by the demo hub network, and which can process and collect the data then. And we will do a field study in the summer where we will have some volunteers that go into a fire simulation facility As you can see it here in the video, for example. And we will then, one big question is still, where do we get the air from? We will include another air tank into the jacket, like a 0.5 liter air tank, which is hopefully okay for the firefighters to carry it with them. We have to find out. And in the end, we want to do some more intersubject variability investigations as well. Thank you very much. Here are all the references I needed in the presentation, and now I'm happy to answer some questions.